Okay, let's continue with the linear differential equation. What we are going to see in this video is a method to convert the linear differential equation into a variable separable differential equation. Why we want this process? Because we already know how to solve variable separable differential equations, but we don't know how to solve linear differential equations. If we find a way to convert this into variable separable, then we can solve it. All right? Okay, now the process is very hard, so I suggest to review this video 2 or 3 times to understand the process. All right, now the person that find out how to make the conversion, he assumed an integrand factor called w of x. All right, now the integrand factor, we don't know what is such integrand factor, but that integrand factor is going to have the capability to have a behavior similar to this part. Okay, now assume that you have the w of x times y. What happens if you have the w of x, that integrand factor that we don't know yet what is going to be the value of that integrand factor, but assume that you have the multiplication of that integrand factor times the y. And also imagine what will happen if you have the derivative respect to x of that multiplication. Okay, according to the formulas that you already know on the derivative of multiplications, derivative respect to x of u times v, you may remember this formula, u derivative of v respect to x plus v derivative of u respect to x. Alright, so that's the formula of the derivative when it is in a multiplication. So assume that you have the derivative of the integrand factor times y. So the result will be the first times derivative of the second one, which is the y, and then plus the y times derivative of w of x, and that is the result. But I'm going to write first the derivative of w of x and then the y. Now, check this out, because this is very important. Check how close these look like. You can see here, this is the same as this, and here the y without the derivative. All right? Okay, so this is very similar. Okay, so can we make them equal? Okay, so but first of all, what we need is to multiply w of x times this thing. So let's do that. And this is just an introduction of what we are going to try to achieve. So let's assume that you have that w of x and you multiply times the differential equation. If you multiply that times the differential equation, is going to be w of x, derivative of y respect to x, plus w of x, p of x, y equal to w of x, q of x. That w of x we multiply times the differential equation in both sides. Alright? Okay, now, what if you happen to have the derivative, again, the same idea as the previous, derivative of w of x times y respect to x. What will be the result of this derivative? It's going to be the first w of x times derivative of y respect to x plus y times derivative of w of x respect to x. I'm going to write first the derivative of w of x respect to x times y. Alright. Now again, how close is these two expressions? Disregard what happens on the left, on the right side. Just focus on here. Now, you can see here that w of x and the derivative of y respect to x, they are here, the same. And here the y is the same as this one. So the only thing left to be this equal to this is that this is different than this. Alright? But these, they are equal, and these two, they are equal. So the only thing to make this equal is that these two numbers, the only thing left to make it equal is w of x times p of x equal to the derivative of w of x respect to x. So we are going to make them equal. Make them equal. You may wonder why we wanted to make it equal. Now, imagine that you are capable to make this equal to this. Because this is equal to this, then this comes from this derivative. So, derivative of w of x times y respect to x, respect to x, equal to the right side, w of x, q of x. And what happens here is that the differential of w of x times y equal to w of x, q of x, differential of x. And just pass the differential of x to the other side. Now, what happens here is that here you have a variable separable differential equation. Alright? And then you can solve it. In this way, if you achieve to make, with this integrand factor times the differential equation, and you achieve to make this equal to this, then you make it variable separable, because here you have only function of x, and here you have only function of this, which is just another variable. There's no problem here, because if you apply the integrants, this integral and this differential, it cancels, right? So there's no problem. Alright, but to do so, what we have to prove is that this is equal to this, so that you can do this step from here to here, but it's not equal, because these guys are equal, the y is the same, the only thing that is not equal is this part, alright? So that is why we are going to make it, or force it to make it equal. So that is why I take this w of x, p of x equal to the derivative of w of x respect to x. Okay, so let's solve this one, because again, remember, we don't know what is w of x, right? We don't know what is. The only thing that we know is that it is function of x. Okay, fortunately for us, this is variable separable differential equations in this way. I'm going to flip the equation. The derivative of w of x respect to x equal to w of x, g of x. I'm going to pass the differential of x to the other side, and the differential of w of x as a division. Differential of w of x over w of x is equal to p of x differential of x, right? Here is just a separation, because this is another procedure. I just took these two, I just took this here. I'm going to solve it. Okay, now this is variable separable differential equation, engineers, because you apply integrals on both sides, and this, the integral of this is the natural lowering of w of x. It's just like integral of the differential y over y equal to the integral of p of x differential of x. Okay, because we don't know what is p of x, we are going to leave it like that, plus the constant. All right. But for the formula, let's assume that the constant is equal to 0. Assume. Okay? It doesn't hurt if you don't assume it to be equal to 0. But let's leave it like that. Okay, now let's clear w of x. Why we want to clear w of x? Because we want to know what is w of x. We are about to know what is w of x. So let's apply the integral, the exponential on both sides. So w of x is equal to the exponential of the integral of p of x, differential of x. With these, engineers, we have found what is w of x. So this is a very important formula that you are going to use to calculate w of x. Now, what is the property of this w of x is that if w of x is equal to this, then you are ensuring that this is equal to this. Now, if you ensure that this is equal to this, you are ensuring that this is equal to this, which is the only thing that is what's left, because the rest is the same. And because now everything is the same, this part is equal to this, then you can go from here to here. And because you can go from here to here, then this is equal to w of x, q of x, and then it is a variable separable differential equation. So this is the formula for the integrand factor. Alright? Okay, let's continue, because we already know what is w of x. So it's no longer unknown. Now we know what is w of x. We just replace it here, and then we can solve it. because this and this cancel, so it's going to be w of x times y equal to the integral of w of x, q of x, differential of x, plus the constant. Now here, don't assume the constant is equal to 0. That was for this integral, right? So that is different. Okay, so let's clear the y. So y is equal to the integral of w of x, q of x, differential of x, plus the constant, divided by w of x, plus the constant over w of x. Now let's replace the value of w of x. The w of x is the exponential. So the y, the general solution is going to be integral of w of x, which is the exponential of the integral of p of x, differential of x, times q of x, differential of x, over here w of x again, exponential of the integral of p of x, differential of x, plus the constant over the exponential, but I'm going to write the exponential in the numerator, exponential of the minus integral of p of x, differential of x. Now, if you remember from the previous video, I told you to keep in mind something like this. If you check your previous video, we have already seen this. This is what we call the homogeneous solution. Right? Is the constant, the exponential minus the integral of p of x. So the linear differential equation is composed by two things. This part of the solution and this part of the homogeneous. The homogeneous always has the constant. This doesn't have the constant. Now, to solve the linear differential equations, you can apply this formula in one row, alright? If you happen to have the linear differential equation like this, you just plug in the p of x here, the q of x here, alright? And then you get the solution. This is a big formula, but I suggest you not to use the big formula because you are going to lose the procedure on how to solve the differential equation, the linear differential equation. Okay, now I know this is heavy because this part is very confusing, alright? But just keep in mind that the linear differential equation, if you apply the integrand factor with this formula, you are capable to do from here to here. And that is what I call the dead step. El paso de la muerte. Because you jump from here and to here. And many students don't understand why, how can you do that? Is it black magic? No, it's not black magic. Here's the demonstration that this is equal to this as long as w of x is equal to this, which is the only thing that was left not equal. Okay, on the next video we are going to solve two problems using the formula of the integrand factor. Alright, see you on the next video.